Hello friends, good afternoon to you all. This is about a data converter, that is analog to digital converter, that is ADC, and digital to analog converter, that is ADC, product understanding for characterization purpose. What is this? These two boxes seem like a heavy or big electrical products or panels. Yes, the right side is industrial transformer choke enclosure. It contains inside it transformer coils. This left side seems like it is the same, but not. It is a analog to digital converter, that is ADC. Actually, it is the first electronics 11-bit analog to digital converter, giving the output at 50 kilosample per second. It was designed using vacuum tube devices, and it is patented and developed by Bernard M. Gordon in 1954 from the company EBSCO Engineering. You can see the size. Its size is 19-inch cross 15-inch cross 26-inch and weight 68 kilogram, consuming around 500 watt power, means 0.5 kilowatt, and cost US dollar 8,000 to 9,000. Just come to the now. In today's world, we have very small devices available in comparison to vacuum tube, that is called CMOS transistors. We have analog to digital converter ADC or digital to analog converter DAC, both up to 16-bit of resolution and output rate around 10 megasample per second. We can see the size is around 0.4 inch by 0.32 inch by 0.06 inch only, consuming 0.2 watt, and it is weight only 10 grams. Cost US dollar 10 to 30 only. So in this way, we have scaled down everything, area, power, by around 64 times, and performance we improved a lot in this 64-year period. However, the earliest recorded data converter is digital to analog converter, and it was actually a hydraulic one, not the electronics. It was found in Turkey during Ottoman Empire to measure the water output to the public. It was designed, and one dam, Mahmud II in Istanbul, is also made using this principle. Why we need data converter? These data converters, as you see in this flow graph, are used for our convenience, happiness, or for our benefit. We know this world is analog. We have some physical analog signals there, like sound, weight, light, gravitational force, etc. If we want to use these analog physical signals for us, for our benefit, so we have to process it, because naturally available is not good. We can improve a lot. So for this we need to process it, and for processing we know that analog processing is not good and efficient. So we have to go for digital signal processing. For digital signal processing, we need these analog signals into digital one. So we can see from physical analog signals from our world, we have to convert it into the analog signals, electrical signal by sensors. Then ADC converts into digital. Then we do the digital signal processing. And to sense these analog physical signals for ourselves, we need back the analog quantity. So these processed digital signal, we have to convert it to analog by DAC, and then these analog electrical signal to back the physical analog signal by some actuators. It can be understood by one example. I'm quoting here, like sound. Sound is there, it's everywhere. So for how we process it, first convert the sound into the electrical signal by a microphone, we all know, and then ADC converts the digital signal, and we do in the computer all the digital signal processing for echo effect, adjust the tempo and pitch, etc. And then we convert it into the analog electrical signal by DAC, and then these analog signal feed to the speaker, which is an actuator, and we listen to our ear. And you can see that today music sounds very fantastic. So this analog to digital and digital to analog converter is very important in many applications. How these, just in a broad way, in a very you can say in a crude way, we can say that the this continuous thick signal can be represented into the digital by dividing it into some discrete levels, and then these discrete levels called the digital output, it can be converted into the analog again by assigning them some analog quantity, and can receive the continuous time analog signal. So it's look like that. In the digital we have the discrete time, discrete amplitude, and in analog we have the continuous time and some continuity at the output also. So now in the converted signal we have the some noise, as because we are not converting it into some infinite number of levels. We have some discrete levels, some available depending on our hardware. So the loss of signal information can be measured through data converter specification, and these are resolution, which is the number of bits, differential nonlinearity DNL, integral nonlinearity INL, signal to noise ratio SNR, signal to noise and distortion ratio SNDR, and then effective number of bits ENOM. What is resolution? Resolution is the number of levels, discrete levels, in which we can represent our analog signals. These are as fine as we can, so means we can maintain the signal information, but there is a limitation. We cannot go for very large number. As we can see, these, if there is a suppose 10-bit resolution, the number of discrete levels is 2 raised to the power 10, which is 1024. So we can represent in 10-bit any analog signal into the 1024 levels. And these analog signal can be at one maximum full scale range, because there is a limit somewhere that we cannot convert efficiently higher than this voltage. So that maximum voltage which decides the actual performance for the data converter is called the full scale range, and the number of levels and the value of one unit is called the least significant bit. These are the terms which are defined in the literature, and we know by these names. So after resolution, there is a differential nonlinearity, DNL. Actually, every one unit, for example, in ADC, one LSB change in the input change the one code at the output. Similarly, for the DEC, every consecutive code change produces the one LSB change in the output. So if one unit change in the input not resulting in the one unit of the output, then there is some error. So this error is represented in the differential nonlinearity. Ideally, it should be 0. So suppose if my half unit in the input changes the 1 unit at the output, it means there is a half unit error. So we can call the 0.5 LSB DNL. INL is the actual transfer curve deviation from the ideal transfer function line. So what is the maximum deviation, we represent it in the INL. So this INL is the summation of or integral of the differential nonlinearity. Next is we know the noise is everywhere. If there is a noise and the signal, so the signal and noise resulted into the noisy signal. And we know that we have the one signal and rest is the noise. So what is the signal strength out of the noise is called the signal to noise ratio. Here one thing is important to mention, that in SNR we exclude the harmonic distortion. What is the harmonic distortion? Actually, noise is random in nature, but sometimes in the converters or in any system, some noise is the predictive, is the deterministic. Like if we are having the one clock, so maybe the in relation of the clock there is some noise. Actually, noise is the everything other than signal, but some noise is predictive, is repetitive. So if we know these repetitive or deterministic noise, so we cannot we can remove it, we can get rid of it. So sometimes some application needs that we can deal with these harmonic distortion because this is deterministic, but you have to tell us the random noise. So this SNR will come into the picture. Now another one is the signal to noise and distortion ratio. In the previous slide, I mentioned that sometimes this deterministic noise is excluded because in some application it can be removed. But here in some applications, some product needs that they want other than signal, everything should be treated as a noise, and we want the signal power to the everything noise and distortion ratio. Here we exclude the DC because DC is the straight line. Okay, and the last is the effective number of bits. Actually, effective number of bits is actually a indication of quality of data converter. Means it tells us what is the noise content and what is the signal contents, and it is directly related to the SNDR we explained earlier. So effective number of bits is the uh, uh, SNDR minus 1.76 divided by 6.02. So this is the actually a ideal bits of the data converter where we can assess the signal purity. So in the conclusion, I can summarize that we covered the resolution, DNL, INL, SNR, SNDR, and INO. I'm sure it helps to measure and debug the data converter more efficiently during the characterization. And we all know that qualitative and good characterization report is very important to showcase your product in the market. Thanks to you all for listening it patiently, and you know that listening is the beginning of understanding. Thank you.